Okay, welcome back everyone. In this video we're going to be talking about binary. And I know I've been foreshadowing this video for a while, so I am excited to finally get to it. So if you've watched any of the before you watch videos that I've been posting in the description thus far, I posted a couple in binary and kind of explained at a high level what binary is. But if you haven't watched those, basically binary is the numerical system that our computers use, to store data and information in memory. Now, binary is what's known as a base 2 numerical system. What you're probably used to is base 10, which we're going to talk about first as kind of a prelude to binary. So base 10. So you know base 10 numerical system as having, so if we draw a little grid here, we have our ones place, we have our tens place, we have our hundreds place, we have our thousands place, and the list goes on and on and on. So we have tens of thousands and then 100,000 and so on and so forth. So, for example, if we had a number, let's say 1221, we know that 1 is in our ones place, 2 is in our tens place, 2 is in our hundreds place, and 1 is in our thousands place. So basically, each digit in the number, so we have 4 here because this is made up of 4 different digits, 1, 2, 2, 1. Each digit's place should be 10 times more than the place to its right. So 1,000 is 10 times more than 100. 100 is 10 times more than 10, and 10 is 10 times more than 1. So basically what our digits in our number mean now, so like for example our 1 here, we're basically saying that we have 1 of the ones place. 2 here is basically saying we have 2 at the tens place, so we really have 20 here. This 2 is basically saying that we have 200, so we really have 200 here. And then this 1 is basically saying we have 1,000, so we just have 1,000 here. So where does the name base 10 come from? If we draw some exponents here, some numbers with powers, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. Well, for a number to an exponent, the number below the exponent, this is known as a base. So, for example, we know that 10 to the 0, or really anything to the power 0 is always going to be 1. Hence, our ones place. 10 to the 1 is going to equal itself, so that's 10. 10 to the second, we know this is going to equal 100, because that's just 10 times 10. Hence, our hundreds place. And finally, 10 to the third is going to equal 1,000. Hence, our thousands place. So that's where the name base comes from. When we say base 10, it's because each of these places, so like our ones, our tens, our hundreds, our thousands, comes from taking 10 to a certain exponent, and each time we move to the left, the exponent just increases by 1. And that's where we come up with these different categories for, I should say, the values in each of the different places in a base 10 number, which we use here as an example, 1, 2, 2, 1, 1,221. And so this is the numerical system you work with on a daily basis. You've probably seen this in math class. I mean, even just basic counting. This is the standard numerical system that we use day to day. And another way you can think about it too is that in our base 10 system, each place, so our ones place, our tens place, our hundreds place, our thousands place, it has 10 different digits that we can put there, representing the quantity of that place. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh, 8, and then 9. That's 10 digits total. And so then once we get to what would be our tens place, we don't have another digit that represents the value 10. So that's why we then add another digit to the end. So now we have 2 digits. So basically, we now tack on this extra digit in the tens place instead of just the ones place. So this represents that we have one quantity of 10 now in the tens place. And so when we talk about binary, binary. Binary is what's known as a base 2 numerical system. Base 2. Now in a base 2 system, there's only 2 different digits as opposed to the 10 different digits we saw here, 0 through 9, that we use, that we have available. And that is 0 or 1. 0 or 1. Now in a computer, 0 basically represents, well, both of these represent different states, but 0 represents the state off, and 1 represents the state on. Now, if you looked all the way down to a hardware level, it would make a lot more sense why 0, for example, represents off, and then 1 represents on. But we're not going to get to the hardware portion in this video. I will hopefully make a video on that later on about registers and arithmetic logic units and all that stuff. But I just want to get the basic concept of binary down for now so we can get rolling with the C++. So just like how in base 10, so we had the thousands place, for example. Well, we know that each time you move to the right, we move one place to the right, the number directly to the right of a particular number's place had to be 10 times less than that number. So, for example, 1,000 again is 10 times more than 100. 100 is 10 times more than 10. 10 is 10 times more than 1. Well, in base 2, each number directly to the right needs to be 2 times less. Or you go the other way around with that and say that each number directly to the left needs to be 2 times greater than the current number. So, for example, if we draw another grid like we did above for the tens, we would have a ones place, a twos place, a fours place, and an eights place, if we were only going to use 4 digits. Now, binary is weird in that you can have leading zeros in a whole number, in a number. So the zeros are actually significant to represent in the number. I know that usually, if you had a number in our typical base 10 numerical system, like it looked like this, well, these digits you would usually just ignore and say, like, these aren't, these don't make any sense to be here, and we would just have the number 10. Well, in binary, these actually are significant, so we do want to keep those around. So if we had a number like this, so 0, 0, 1, 0, and we map that over here, we have 0, 0, 1, 0. What we actually have here, this number would actually equal 2. Because we have a 0 in the eights place, so we have 0 eights. 0 in the fours place, we have 0 fours. We have a 1 in the twos place, so we actually do have something that equals, that's equal to 2 here. And then we have a 0 in the ones place, so that would be equals to this whole number 0, 0, 1, 0 would actually equal 2. And again, this numerical system is called base 2 because if we again think about this in terms of exponents, we have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and again we're just incrementing the exponent by 1 every time. 2 to the 0, anything to the 0 power always equals 1. 2 to the 1 equals 2. 2 squared equals 4. And then 2 to the third would equal 8. And so you can see if we map it back up here, we have 1 for ones place, 2 for the twos place, 4 for the fours place, 8 for the eights place. And it's called base 2 again because 2 is our base for the exponent. Now let's do another example here real quick to clear this up. Let's say we had another number that was 1, 0, 1, 1. So how do we figure out what this equals, what this binary number is equal to? Well, let's think about what we talked about above. This, since the least significant digits are on the right, and then moving to the left, we have more and more significant digits. So this 1 here, this first 1 would be our eights place. This would be our eights place. And so this next 0 would be our fours place. This next 1 would be our twos place. Get a little bit cleaner. And then this last one would just be our ones place. So how we can think about this then is we can say, okay, we have a 1 in our eights place, which means we have an 8. We have a 0 in our fours place, which means we're be adding 0 here. If this was 1, we would actually be adding 4 here. In our twos place, we have a 1. In our twos place, we have a 1, so we will add a 2 here. In our ones place, we have a 1, so we'll add a 1 here. And so we add this up, and we would get 11. So this binary number is actually equal to 11. If we did one more, where we just had 0, 0, 0, 1, and we only had a 1 in our ones place, this would equal 0, since we have a 0 in our eights place, plus 0, plus 0, because both the 4 and the 2's place are also 0, plus 1, which would equal 1. And again, the reason being we have 1 here is because the only digit that was a 1, not a 0, was our ones place, which is why we see a 1 here, because that means we have 1, 1. In our ones place, we have a quantity of 1. And then in the 8's, 4's, and 2's place, we add 0, so we don't add anything. Only when you see a 1 do you add the value of the place, which in this case was our ones column, so that's why we added 1 and got the value of 1. Hey guys, another way to think about this that I realized I had missed after I had finished recording, if we take that example of 0, 0, 1, 0, again, where we knew that this was equal to 2, just because we knew that this was basically 0 plus 0 plus 2 plus 0, which equals 2. Another way you can think about this is if you look at the bits in a certain binary number, so where we have 0, 0, 1, 0. Another way we can calculate this is by basically taking each bit and multiplying it by the base, which is 2 in this case, the base to the particular power of its position that it's in. So how we said our first bit here was 2 to the zeros place, which is just ones. This is our ones place. Our next bit here was our twos place, right? Which is really just 2 to the first. And then the next place is 2 squared, which is our fourth place. The next place is 2 to the third, which is our eighth place. And so really what you can do, if we start from the left and move right here, we can take, so since we have a 0 here in our fourth bit, our leftmost bit, we can do 0 times, 2 to the third, which is, again, just 8, plus 0 times 2 squared, which is just 4. This is our 2 squareds place, or our 4's place, plus 1 now, since we have a 1 in our 2's place, 1 times 2 to the first, plus 0, because we have 0 in our 1's place, 0 times 2 to the 0. And then you would basically just simplify this out, do the addition, the multiplication and addition, and that would give you the same result essentially as 2. So if we did another example, right, where we had, let's say we had something more like 1, 0, 1, 0. Well, in this case, then we would have 1 times 2 to the third, which again is just 8, plus 1 times, or excuse me, I'm sorry, 0 here, not 1. Let me back that up here. 0 times 2 squared, so we have a 0 in our fourth place. I'll map these out too just to make it more clear. Plus 1, that you have a 1 in our 2's place, times 2 to the first. So this 1 is going here. And then plus 0, since we have a 0 in our 1's place, 0 times 2 to the 0 power. So this would go to here. And then again, you would simplify this all out, and you would see that this would end up being 8. This would end up being 2, 0, and 0. So you add these together, and you get 10. Now, if we added, so we're only working with a 4-bit number here, but if you added more bits, like you had an 8-bit number instead, so you had 0, 0, you had 0, 0, 0, 1, and we had 1, 0, 1, 0. This first part here is just what we did above here. But if you wanted to add on this bit now, this 5th bit, that would be 1 times 2 to the 4th power, and then these would all be 0, so it would be like 1 times 2 to the 5th, 1 times 2 to the 6th, 1 times 2 to the 7th, and so on and so forth. And that's just another way you can think about how to basically compute these binary values and convert it into decimal. Now, it's important to note, and I'm going to draw another binary number here, 1001. Each digit, each individual digit in our binary number, so 1 would be a digit, 0 would be a digit, 0, so on and so forth. Each individual digit is known as a bit. A single digit is known as a bit. So 1 would be its own bit, 0 would be a bit, this 0 would be a bit, and then this 1 would be a bit. And again, each bit can be either 0 or 1. Now in binary and computer science, we have names for certain groups of numbers of bits. So for example, how we talked about a single digit in binary is called a bit. A group of 4 bits is called a nibble. Now, if we added more bits onto this number, so let's say we had 8 bits instead of 4, so we'll say another 1, 0, 0, 1. So 8 bits, or 2 nibbles, is actually what's known as a byte, and this is probably the term you've heard more often if you're kind of somewhat tech savvy. Byte's probably the term you've heard most often, like gigabyte, kilobyte, megabyte. This is often what we measure certain sizes of things as on a computer, certain sizes of files, pictures, videos, etc. So for example, on this right, mega for megabyte, a megabyte is actually 1 million bytes. So if you wanted to know how many bits this was, how many bits were contained in this, which is our single digits here, 1 or 0, we could just multiply this by 8, which would give us 8 million bits. So when you think about how many bits, so if we measured instead of measuring in megabytes, if we measured how many bits that was, there would be 8 million bits in a byte, since each byte contains 8 bits. So now if I can clear the page here, in computers there's another term known as words. Words in a computer. Now words is basically another grouping of bits, but the number of bits in a word varies from processor to processor and system to system. That being because if you ever heard of like a 32-bit operating system versus 64-bit operating system, it has to do with how much addressable memory is possible with that specific operating system and processor. So some systems, registers, can hold 32 bits of information, some can hold 64 bits. And normally the size of a word then in a specific system or computer varies depending on that addressable memory size. So for example, on a 32, we'll just, in general, we'll say on a 32-bit system, one word would equal 32 bits. Likewise, on a 64-bit system, it would probably equal 64 bits. One word would equal 64 bits. And so again, binary, bits, bytes, this is all how computers basically store and represent data and instructions that it's going to use, that it maybe needs during a particular program is running. It basically stores all of these ones and zeros, and these ones and zeros then it translates to information it can actually use while the program is running. So let's discuss now how different data types are represented in C++. We have our integral types, which are our shorts, our ints, our longs and long longs, and then our floating point types are our floats, our doubles, our long doubles. And let's talk about why our integral types can represent a certain range of values, if you remember how we talked about that. So I have it calculated here. A short, for example, can represent 65,536 different values, whereas with our floating point types, we're more concerned with the precision, the amount of precision of like the number of decimal places, for example. And so let's see how that's all represented in binary. So if we start off simple, let's start off with our short data type. if you remember that from earlier episodes. Short data type was typically the smallest integral type we can represent in C++ on a particular system. So on many systems, shorts are represented. If you remember, we talked about this a couple episodes ago. It's represented typically by about 2 bytes. 2 bytes. And if you remember from the discussion we had just a little bit ago, a byte is really 8 bits. So this is really 2. Make it look cleaner. 2 times 8 bits, which is just 16 bits. And so we know that a short can represent 65,536 different values, so 65,536 different values. And so why is that? Well, if we write out our 16 bytes, and I'm gonna separate these into nibbles, which again is just a grouping of 4 bits. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10, 11, 12, 13, 14, 15, 16. So these are 16 bits. This is the number of bits that makes up a short data type in C++. Now right now we have them all set to 0. So ultimately, if we looked at this and we knew this was a short and we were trying to figure out the value of this number, we could say this is equal to 0 because all the bits are equal to 0, which means we would just have 0 plus 0 plus 0 plus 0, etc., which would just equal 0. Now let's say we came in here and let's erase, let's erase this first bit here, our least significant bit, and let's replace that with a 1. So if you remember, this is the first bit here, our first bit, this is our ones place. And then remember, each bit then moving to the left increases by 2, by a factor of 2. So this would be our 2's place. This would be our 4's place, because again, binary is base 2. It's a base 2 number system. Then we have our 8's place, and this would just continually increase by a factor of 2 as we move left. And again, if you remember, because in base 2, if we had 2 as our base, then we had 0 as an exponent for the first bit. This is where the first I should say, place in a base 2 number system comes from, because 2 to the 0, any number to the 0 really, again, is 1. So that's where our ones place comes from. If we took 2 to the first power, that would just equal 2. Hence where our 2's place comes from. And then 2 squared, we all know that equals 4, because that's really just 2 times 2. So we have 4, hence where our 4's place comes from, and so on and so forth down the line. So now we return to the question of how do we get that shorts can represent 65,536 different values with 16 bits. Well, again, if we have a 1 in our ones place, we know that this is no longer going to be 0. There's a 1 in our ones place here for that bit. We know this is going to equal 1, because it's going to be 0 plus 0 plus 0 plus 0 plus 0, 0, 0, all the way down to the end until we get to the ones place, and then that's just going to be plus 1. Likewise, if we just take out a random number here in the first nibble, let's say that for our 8's place, our bit that represents our 8's place, we had this. Well, now what we would have is 0 plus 0 plus 0 plus 0 plus 0, and then in the last nibble we would have 8 plus 0 plus 0 plus 1. So this would actually equal 9. If we had 1 here in our 8's place and a 1 here in our 1's place, it would actually equal 9. So likewise, this, that trend will continue. So for any bit here that we replace with a 1, we basically would just add that to the total of the result. So for example, let's get rid of this 1 here, and let's get rid of all of these zeros. And so I've just gone ahead and replaced all of the 0 bits with 1s. So now all of our bits in this short, these 16 bits, these are all 1s now. So if we follow our rules from how to figure out and how to translate, or I should say convert a binary number to a decimal number, the corresponding decimal number, since these are all 1s, what we would have is 32,768 plus 16,384 plus, and then we would just continue down the line. So plus 8,192 plus 4,096. So I'll just do dots to represent all of this, all the way until the end where we would have plus 1, because we even have a 1 in our ones place. So this would be plus 8, plus 4, plus 2, plus 1. So we basically would add all of these numbers together that we see up here on the top row, all of these numbers. And so if you took a calculator and added all that together, what you would come out with is 65,535. So this right here, with 16 bits, this is the maximum number. This is the maximum number that we can represent with 16 bits. So if we compare it now to the range of values that we can represent with 16 bits or short, you'll notice that these are off by 1. And why is that the case? Well, because if you think back to our absolute minimum value, which is where all of these were 0, which we know then that if we have all zeros, we know that the result's going to be 0. So our range of values that we can represent, since 0 is our minimum and 65,535 is our maximum, is 0 to 65,535. This is a total range of 65,536, because we can go from 1 to 65,535, but then we also have that 0 that we can represent with this as well, which is where we get that the 6 from. And as a little side bit of information, a very quick and dirty way to figure out how many different values you can represent with a certain number of bits, if you take base 2, because we're in base 2, if you take 2 to the power of the number of bits that we're using, which in this case is 16, 2 to the 16, you'll actually get from that, if you put that into a calculator, you'll get 65,536, which is, of course, again, the range of values that we had up here before. And so the same really applies then to any of the other data types. The same exact rules apply. So, for example, we know that our integers, our ints in C++, we know that those are typically, in a lot of systems, represented by 4 bytes. 4 bytes. Which again, the number of bits then, we would just do 4 times 8. And that would give us 32. A little bit, 32. So we would have 32 bits that represent an integer. And so again, we could do all the same work we did up here with the short for a short, down here for an integer, and you would see that all the same ideas, the same rules for binary apply, obviously, because this is all in binary. But if we want to calculate real quickly, the quick and dirty way to figure out the range of values in an integer could represent, if we just did 2 to the 32nd, well, if I pull over my calculator here and we'll do a clear all, we'll just do 2 to the 32nd, and there we have it, 4,294,967,296 different values we can represent with an integer that is made up of 32 bits. And so if you remember our discussion in the video about signed and unsigned types, how if we had unsigned, unsigned types, and actually, let's just so I can get some more space, I'll actually do that down below. Unsigned types, we know the rule for that they have to be greater than or equal to 0, whereas signed types can be positive or negative or 0. So if we think about the range we calculated for our short here, our range of values is 0 to 65,535. So what we actually represented here was an unsigned data type, because our range only goes from 0 to 65,535. So this is how a computer would store an unsigned data type, not a signed data type, but only an unsigned data type. Because as we'll see, the computers actually have to find a way, they actually have to have a way to represent negative numbers. Because with this, the way we have it set up here, we have no way to, computers have no way to conceive of what a negative number is. Since this value is always going to be, or I should say the result of these binary numbers that we've learned so far are always going to be 0 or greater, which means they're going to all be unsigned types. So how do computers know when a number is supposed to be negative? How can they get a sense of uh, a positive number versus a negative number? Well, they do this using a certain technique called 2's complement. 2's complement. 2's complement. And this is how most machines store sign types in binary. But before we jump into what 2's complement is and how we work with it and how to represent binary in 2's complement, we kind of need to talk about the history of how we came to 2's complement in the first place. So if we pretended like we had a data type, so like for example, our short data type was 16 bits. Let's pretend that we have a data type that's just made of 4 bits. 4 bits. We have 0, 0, 0, 0. So we had a data type that was only made of 4 bits. This would really technically be 1 nibble too, but just 4 bits is all we have. So we know that the result of this, because we have our 1's place, our 2's place, our 4's place, our 8's place. The result of this would just be 0. We already know that. And of course, likewise, if we had 0, 0, 0, 1, it would be equal to 1. If we had just 1, 0, 0, 0, this would be equal to 8. And we know how to do, convert binary to a decimal number. We've done it before. We did it up here above, so that's all fine and dandy. But now, what if we said, how do we represent, for example, a -1? How do we represent a -1 in binary? Well, given what we know so far, we have no way to represent a negative number because we know that no matter what we do with these bits, it's always going to be equal to a 0 or a positive number. So one technique that was thought of was, let's take the greatest, or I should say the most significant bit, which would be 8, our 8's place, and let's let this represent the sign of the value, the sign of a number. So, for example, if a number was, if the 8's place here was 0, this would actually be a positive number, but if it was 1, this would actually be a negative number. So if we wanted to represent -1, we would make the most significant bit 1, so we know this number is negative, and then we would have 0, 0, 1. So we would do our normal addition here, so we would have 0 plus 0 plus 1, because that's in our 1's place, and this would be equal to 1. But since the most significant digit here is a 1, we know this is a negative number, so we would tack on that negative sign here at the end. So really, you can almost think of it like this, where we have a negative sign on the outside, we do the addition first. And that brings us to -1. Likewise, what if we wanted to compute, let's say, -5? How would we represent -5 with this most significant bit being the sign strategy? Well, since we know it's a negative number, our most significant bit is going to be 1. And then to get to 5, we know we can say that we'll set our 4's place to 1. We'll set our 2's place to 0. And then we'll set our 1's place to 1. So we would have 4 plus 0 plus 1. We can make that whole thing negative, and that will be equal to -5. And then likewise, if we needed a +5, if we needed a +5, we would just make our most significant bit 0, then we would just have 1, 0, 1 like before. So now we just have 4 plus 0 plus 1. We know this is going to be a positive number because of the 0, and that would just be equal to 5. Now you'll notice something now, is that because we're using the most significant bit, so our 8's place here, as sort of our sign bit that determines whether our number is negative or positive, you'll notice that we lose a bit of our range on the positive end of things. So before, when we had all 4 bits representing a part of the number, so for example, if we had 1, 1, 1, 1, and this was not a signed bit, this was just a regular bit that like we were doing before with unsigned types, we would have 8 plus 4 plus 2 plus 1, which this would be equal to 15. But now, the highest number that we can represent in a positive number, so for example, let's say this was 0 instead of a 1, and this is a signed bit now, the largest number we can represent that's positive is 4 plus 2 plus 1, which is equal to 7, positive 7. So you can see by using that the most significant bit as a signed bit, we lose a bit of range on our positive end of the spectrum. So now we can only go to positive 7 with 4 bits instead of 15 as we did before. But as a trade-off, though, now we can represent negative numbers as well. But on the other hand, you know, we can still represent the size of the range of numbers we can represent is still the same. We can still represent 16 different values with 4 bits. The only thing really that's changing here is the amount of positive numbers that we can represent. So the range of values we can represent now, so before it was, we could represent anywhere from 0 to 16 when we didn't have that sign bit. But with the sign bit now, the range we can represent changes from negative 7 to positive 7, which is still 16 values in total. And actually I have this wrong here, this shouldn't be 16, this should be 0 to 15, but we can represent 16 values total for unsigned integers. And likewise for the signed data type here, we can represent 16 values here as well. It's just now we also have that negative end of the spectrum piece in there. And hey guys, something I screwed up on in the video there, something I wasn't quite correct on. When we're working with signed bits, I know that, so for example, we're working with a 4-bit binary number. I said that the range of values is negative 7 to positive 7, which is actually incorrect. It'd actually be negative 8. It would actually be negative 8 to positive 7. And the reason being is because, for example, if we had what we had before, we had 1, 1, 1, 1, again working with a 4-bit number here, this would equal negative 7, and that's true. But if we wanted to represent negative 8, we could actually just do 1, 0, 0, 0. So if just the most significant bit is 1, it would represent the negative of whatever this number would usually be in unsigned binary. So this would be negative 8, for example. And you can do that with any number of nibbles and bits and stuff. So, you know, if instead we had 1, 0, 0, 0, and then 0, 0, 0, 0, if just this most significant bit was 1 here, this would equal negative, and I think that's, what is that, negative 128, I believe. I had it pulled up on my calculator here. I think that's negative 1. Yeah, negative 128. And so that's why we can actually represent one more than I had said originally here. So it's negative, if we're working with 4 bits, if we're working with a 4-bit binary number, we can actually represent negative 8 to positive 7. So I had said for this that the number of values that we could represent was 16, and that still holds true here. Because I know when I said negative 7 to 7, that's only 15. You know, that's only 15, and that's not correct. You can represent negative 8 to 7, and that would be 16 values in total that we can then represent, since we have negative 8 to negative 1, and then 0 to 7, which is 16 values. And if you go back to my video on signed and unsigned types, we sort of made that graph out that shows how, you know, when you switch from using a unsigned type to a signed type, for example, so here's our 0, here's our negative numbers, our positive numbers. Whereas with unsigned types, right, we kind of represent this range of values. When we switch over to a signed type instead of an unsigned type, the range that we represent then sort of shifts to something more like this, where we have an even number of positive numbers, an even number of negative numbers we can represent, and then of course 0 as well. Now this is all, you know, fine. We can store negative numbers in binary using this, you know, most significant bit strategy, where we make that the sign bit, with 0 being positive, 1 being negative. And so that works fine if we're just storing it in memory and we retrieve it and we read the value. But we'll soon find out that this actually doesn't work. And the reason it doesn't work is because when we do binary addition, or subtraction, whatever you'd like to call it, when we add a positive number and a negative number together, we'll see that the values we get are disjunct. It doesn't work. And we'll actually show how to do binary addition right now, and then I'll show you what happens when we add a positive number with a negative number in binary, and we'll see exactly why this doesn't work. And then we'll have some more strategies to mitigate that problem, so that we can do basic arithmetic with binary. So let's make things simple here, and let's start out with a simple addition of two positive numbers in binary. So let's say that we wanted to add, we'll say 2 plus 2. And we know in decimal this is going to be 4. And from that, 2 plus 2 is going to be 4. So in binary, it should be written as 0, 0, 1, 0 plus 0, 0, 1, 0. And we know that because this is the ones place, so we have 0 here. In the twos place, for both of these, if we're doing 2 plus 2, we're going to put a 1 there. So we really have 2 plus 2, and since the rest of these are 0, the result for both of these binary numbers individually is just 2. So again, we basically have here 2 plus 2, just in binary. So let's do the addition here. To do that, we just take this column by column, or I should say place by place, just like we do with decimal. So first we'd add at the ones place, which would ultimately just be 0. We have 1 plus 1, and since in binary we only have 0 or 1 representing each place, the value in each place column, this would actually just be 0 here, and we just carry the 1. And then so we have 1 plus 0 plus 0, which would just be 1, and then we have 0 here. So just 0 plus 0. And so ultimately then what do we have here? Well, from the previous examples, we know how to translate a binary number to a decimal number. And we also know that since we're now using the most significant bit as the sign bit, meaning whether it's negative or positive, so we know that 0 indicates that it's positive. We don't have to write this unless we only have to write the sign really if it's a negative, but we'll just write a positive there to get the point across. We know that there's a 1 here in our fours place, which means that we add a 4 here, and then we have put a parenthesis there. Then we have a 0 in our twos place, which means we add 0 to the number. And we also have a 0 in our ones place, so again we can just add 0 to the number. And again, I'm putting this in parentheses to separate it from the positive sign here. And so ultimately this would just equal 4, which is exactly what we were looking for, because 2 plus 2 equals 4. In binary we do the same exact addition and we come out to 4. Now let's see what happens when we do the same thing. We do another addition problem here. But instead of adding positive 2, let's add negative 2. Let's add a negative 2. And so here, what would we expect? Well, we would expect to get 0, because basically when you do 2 plus negative 2, you're just doing 2 minus 2, which would ultimately be 0. So if we do this again in binary, we again have 0, 0, 1, 0, which is 2 in binary, and then negative 2. So since we have negative 2, we know that the first bit, again, the most significant bit, or the farthest bit to the left, which is our sign bit, needs to be negative, which is 1, for using it as a sign bit. 1 means negative. And then we would go 0, 1, 0. So this is 1, 0, 1, 0. If we're using the most significant bit, again, as a sign bit, this is negative 2 in binary. So let's go ahead and add these together like we did before in the example above. So we get 0, here we get 1, 1, which means we would get 0 here and we carry the 1. Then we would get 1, 0, 0. So we would have 1 here, and we have 0, 1. We have 1 here. And you'll see what this actually comes out to is in fact not 0. So if we do the, if we translate this binary number here to its decimal representation, we know that since we have a 1 in the most significant bits place here, in our what would be our eighths place, we know this is a negative. Right, parentheses here. In our fours place we have a 1, so we'd be plus 4 plus 0 in our twos place, so plus 0, 0 in our ones place, plus 0. So this would ultimately come out to a negative 4. So that doesn't make any sense, right? Because we know over here when we did the decimal arithmetic, we saw that 2 plus negative 2 equals 0. Well, that most definitely does not equal negative 4. And so you can really try any combination of positive and negative numbers, and you'll notice that for the most part this never works. When working with negative numbers, when using signed binary numbers, meaning 0 is positive, 1 is negative, it doesn't play well when doing arithmetic, when you have positive numbers and negative numbers together. And so this whole strategy of using the most significant bit as a signed bit really doesn't play well. It works well if we're just storing a number. So, if in computer memory we had a bunch of zeros and ones here, and this is just a random, sort and array of binary numbers here in bits. But let's say, for example, that, we were coming through here and we were just looking for our number 5 that we stored somewhere, and our computer comes across this sequence of bits here, and we know that it's 4 plus 0 plus 1 with the positive over here, and we know that's equal to 5, right? And then we can do the same thing for a negative here, right? So if we were looking for a negative 1 that we had stored, which this would ultimately be negative 1 here in our computer memory, we have negative 1 here. And so there's a 1 in our ones place and a 1 at the negative in the sign bit, which means it's negative. So that works fine, if we're just retrieving it from memory and from a random sequence of bits. But when we come over here then to try and do arithmetic between positive and negative numbers in binary, you can see then that it doesn't play well. So ultimately then, even though we can retrieve and store these negative and signed values in signed binary values in memory, we ultimately need a better way, a better strategy to then do arithmetic on these operations, because we do arithmetic all the time in computers between different binary numbers to both carry out operations, to perform particular equations to get certain data back, and there's this so we need a better way to play with these negative binary numbers and positive numbers. And please don't get too distracted by how computers know where to grab certain values in memory. This was just a total random example of a random sequence of bits. There's different ways that computers can basically know where to look for certain values in memory, but this was just an example, so don't take this to heart here. This isn't exactly how computers would grab data from memory, but this just gives you a general gist of what I'm talking about, though, as far as being able to retrieve negative and positive signed binary values, but not necessarily carry out arithmetic operations on those values. In computers, a lot of places in memory are addressed. There's an address specified with certain locations in memory. So like here for a positive number, here for a negative number, for example. And so since they're addressed, computers know where to look for that data in memory. A particular value in memory. But we'll talk about addressable memory later on in this series, so don't worry about that too much right now. So let's real briefly here recap this sign bit strategy. Just write sign bit. The strategy of basically taking that most significant bit, the farthest bit to the left in a binary number, and making it the sign bit so we can represent positive and negative values. So, on the plus side, I'll draw a little smiley face here. On the plus side, we'll say we can now represent negative, let's put negative numbers. So that's cool, right? We have a way to basically represent negative numbers using that sign bit to declare, if it's a 1, it's obviously a negative number. If it's a 0, it's a positive number. We can store these in memory, we can retrieve them, and we can read them correctly. Now on the downside, put a little sad face here. On the downside, I'll just say, we'll just write down arithmetic. We'll say arithmetic, no good. It doesn't play well with arithmetic when you basically are working with trying to add a positive number and a negative number together with that sign bit. So although we can represent negative numbers now and it works for those means, when it comes to arithmetic, and which means adding again negative numbers and positive numbers, it does not play well. So we need another strategy in order to do so. So the next strategy that came along, the next sort of way of doing this was called one's complement. One's complement. And so the basic algorithm for representing a number, a binary number that is, in one's complement is actually quite simple. So let's say we have a 4-bit number, and we'll say we're trying to represent 2 in binary. So we have 0, 0, 1, 0, which we know is equal to 2. So we have a 1 in our 2's place and a 0 in all the other places. So if we wanted then to represent -2, by the rules of one's complement, the algorithm of one's complement, in order to represent a number, the negative number of 2, for example, so -2, what we would do is we would flip all of the bits to be the opposite value that they are currently. So zeros would become ones, and ones would become zeros. So here, if we wanted to represent -2 in one's complement, we would take the the binary representation of 2, of positive 2, and flip all the bits. So we would say this is now 1, 1, 0, 1. Because we have a 0 turned to 1, 0 turned to 1, 1 turned to 0, and 0 flipped to a 1. And now this would equal -2 in one's complement. This is how we would represent -2 in one's complement. And I know what you're thinking, right? So if our most significant bit still represented the sign bit, right, so this would be a negative number, what we would have here is negative, we have 1 in our 4's place, it would be 4 plus 0 plus 1, which would equal -5. And obviously -5 does not equal -2. So just bear with me here for a moment, and we're going to explain why one's complement is represented this way. Now the same applies for any number in binary. So let's say now instead we wanted to represent a positive, let's say positive 5 in binary. So we have 0, 1, 0, 1, which we know this is equal to 5. So if we wanted to represent -5, the negative of that number in binary, we would just flip all the bits. So we would have 1, 0, 1, 0. And this would be how we represent -5 according to one's complement. And so over here to the right of the screen, I've gone ahead and I've written out all of the numbers, how they would be represented from 0 to 7, and then of course all their negative representations, how they would be represented in one's complement. So you can see here, for example, for 0 in binaries is 0, 0, 0, 0. So if you flipped all the bits, you would actually have this weird -0 here, where we'd have 1, 1, 1, 1, because we flip all the bits and then it becomes a -0. So that's kind of a weird, odd property of one's complement. You get this -0 in here, and we'll talk about that in a bit here. 1, for example, in binary is 0, 0, 0, 1. So -1 would be 1, 1, 1, 0. Again, we're just flipping the bits. 2, 0, 0, 1, 0, -2, 1, 1, 0, 1. And you see that sequence, that property carries on, throughout all of the negative numbers. If we go all the way down to the 7 here, we have 0, 1, 1, 1. -7 is 1, 0, 0, 0. All the bits on both are opposite. So if we, for example, wanted to do, if we wanted to do 3 minus 2 in decimal in base 10, we know that we would get 1 from that. The result would be 1. So then in binary, in one's complement, let's do that now in one's complement. So we have our +3, which would be 0, 0, 1, 1, which I am getting from here, 0, 0, 1, 1. That's just 3 in binary. And then we're going to be adding. We're going to be adding basically a -2. So we would have our -2, 1, 1, 0, 1. So 1, 1, 0, 1. We're basically adding a -2 because, again, adding a negative number is the same thing as subtracting a positive number from another positive number. So if we do this math here, and I'm going to make this just a little bit cleaner. They're a little sloppy. So we did 1 and 1. So if we went ahead and did this, we would have 0, so we would carry the 1. Then we would have 0, carry the 1, 0, carry the 1, 0 again, and then carry the 1, which would just ultimately be 1 here. And I'm glad this actually came up real quickly, because if you can see here, we're working with 4 bits for each number, and since the result here is actually 5 bits, this is what's known basically as a carry bit, and since we're only working with 4 bits, we basically discard this final bit. I don't want to call it overflow, because overflow and carry are not necessarily the same thing, but if we have more bits in the result than what we're working with, which again is 4 bits, then we discard that carry bit at the end. And so you can see here our result is 0, 0, 0, 0, which ultimately equals 0. Now, 3 minus 2 we saw in base 10 equals 1. And so it's close, you know, we're close here, but we're not quite correct. We seem to be 1 off. If we go back over here to our layout of our numbers, we can see that we're 1 off. You know, we got 0 as a result, but we needed 1. So let's do another one. Let's make it a simple one. Let's just do 2 minus 1. And actually, let's do this. Let's do 2 minus 2. We'll do 2 minus 2. So obviously in base 10 in decimal we would expect to get 0. Let's do that now in binary for 1's complement. So we would have a positive 2, which would be 0, 0, 1, 0. And then we would do plus the negative 2 in 1's complement, which would be 1, 1, 0, 1. So 1, 1, 0, 1. Let's see what the result is. We would get 1, 1, 1, 1. 1, 1, 1, 1. And according to our little layout of numbers here, we see that that's really the opposite of what 0 is. If we flip all the bits for 0, we would get 1, 1, 1, 1, which would become negative 0. We have negative 0. So okay, that's negative 0 is basically 0. It's the same, but we're still, if we look at our layout of our numbers here, we're still 1 off from what we should be. We're still 1 off. Again, if we did over here, if we did 4 minus 2, we have 4 minus 2, we expect to get 2. In 1's complement, if we did that addition or subtraction, if you will, in 1's complement, we have 0, 1, 0, 0. We would add a negative 2, which again, the negative 2, like we saw before, is 1, 1, 0, 1. And so the result would be 1, 0, 0, carry the 1, we have another 0 here, 1, discard the carry bit, and so our result here then would equal 1. 0, 0, 0, 1 is equal to 1 in decimal. And so again, we expected 2, we got 1, and so again, we're 1 off here. We're 1 off from where we need to be. We're close, but no cigar. And so overall, 1's complement seems to work pretty well. We're 1 off every time from where we need to be for our arithmetic. And so if we just added 1 every time to the result, if we just added 1, we'd always come out with the correct answer. We get 1 here. Really, we're not adding 1 to the decimal representation. What we'd really be doing, so if we took this last one, 0, 0, 0, 1, 0, 0, 0, 1, we're actually adding 1 to this, which then this would ultimately become 0, 0, 1, 0, which would equal 2, which is what we were looking for. Looking for over here. And so with 1's complement, when we're doing our arithmetic, basically we just need to add 1 to the result every time, and we'll always come out with the correct result. For the one where we came out with negative 0, where we had 1, 1, 1, 1. So if you just added, if you added here, if you just added 1, we would get 0, carry the 1, 0, carry the 1, 0, carry the 1, we get 0, get 1, discard the carry bit, we'd have 0, 0, 0, 0, and that would give us 0. So instead of negative 0, then we would have 0, which is technically speaking, the result we were looking for when we took 2 minus 2 here. So that would give us our expected result. Instead of negative 0, we would get 0. So, recapping, 1's complement plays fairly well, but it's we still need a better way to do arithmetic with binary, because ultimately we still have that problem of being off by 1 every time we do some sort of arithmetic calculation. You know, in computers, that's a big deal, right? We don't want to be off by one every time. Uh, so uh, so there's actually another way. I'm going to open up a new sheet here. There's actually another method that was created, another way of representing negative numbers in binary, and that is called 2's complement. And this is the form that binary numbers you'll find on most modern computer systems today. Now the way 2's complement works is basically we take the ones complement of a binary number and then we just add 1 to it. So we flip all the bits and then we add 1 to it. So again, let's use the example of having a positive 2 in binary. So we have 0, 0, 1, 0, which we know equals 2. So to get the negative 2, the negative representation of this number, which would be negative 2, basically what we do is we flip all the bits. So step 1 here, we flip all the bits, so it would be 1, 1, 0, 1, oops, 0, 1. And then step 2, we would just add 1 to this number. We just add 1 to this number. And so then ultimately we would come out with 0 here, 1, carry the 1, so 1, and then 1, 1. And so this is how we would represent our negative 2 in 2's complement. 1, 1, 1, 0. Likewise, we'll just use positive 1 as an example. So we have 0, 0, 0, 1, which equals 1. So step 1, we would again flip all the bits. So we have 1, 1, 1, 0. And then step 2, we would again just add 1 to the binary representation. So we'd have 1, and then we'd have 1, 1, 1. This is how we would represent our negative 1 in 2's complement. So again, on the right here, I've gone ahead and written out some numbers of how they would be represented in 2's complement for the negative numbers, and then we have the positive numbers here on the bottom. I didn't go to all the way to 7 this time. I just only went to 4, to negative 4, just to get the point across. But this is how the negative numbers would be represented in 2's complement. Something to notice here is that by using 2's complement, one of the benefits is that we actually get rid of that negative 0 that we had with 1's complement. And the reason being is because we know that 0 in binary is represented by 0, 0, 0, 0. This just equals 0 in base 10 or decimal. So if we took the, if we tried to translate this then to 2's complement, the negative 0, well, we would get, for step 1, we would just flip all the bits, so 1, 1, 1, 1. And then in step 2, we would add 1 to this. Ultimately, what we would get is 0, carry the 1, 0, carry the 1, 0, carry the 1, 0, and then carry the 1, and then you get 1 over here. We would discard the carry bit, so we'd still end up with 0, 0, 0, 0, and so we'd still have 0 as our result when we flipped it to 2's complement. So let's go ahead and do an arithmetic operation with 2's complement. So let's do a simple one. Let's start with 3 minus 2. We'll say minus 2 in decimal. Let's make that a little bit cleaner here to make it more understandable. Minus 2, we would expect to get 1. So let's do 0, 0, 1, 1, and we'll go plus, basically plus the negative, a negative 2, so we would have 1, 1, 1, 0. So let's go ahead and get the result for this. So it would be 1, then we would have 0 here, carry the 1, 0 here, carry the 1, 0 here, carry the 1, and we would end up with 1 here. Discard the carry bit, and so our result would be 0, 0, 0, 1, which ultimately would equal 1, which is exactly what we were expecting and what we got when we did it in base 10 or decimal. And so you can do this for any of these numbers, and it'll come out correctly. You can try any combination of these numbers, and the answer should come out to the correct answer. And so you can see that we encode, we represent numbers in 2's complement in modern day computers, so that way computers can easily perform arithmetic operations on positive and negative numbers, and there's no weird discrepancies. There's no weird thing where they have to add 1 to the result. Our arithmetic plays very well if we use 2 complement to represent the numbers. This is actually something really cool I learned actually not that long ago, a way to think about this in 2's complement that might help make a little bit more sense. If you see that all of the most significant bit, the leftmost bit in all the negative numbers of 2's complement is a 1, so instead of thinking of this as like a negative sign here, since we have -4, -3, -2, -1, instead think of this as a negative of whatever this bit would represent if it were not a signed bit. So, in this case, this would be our 8's place. So think of this always as -8, And really, then, how we come to our result here on the right of what the binary number represents in decimal. So if we take this, this top one here, for example, our 1101, or excuse me, our 1100. What we really have here is -8 plus 4, since we have a 1 in our 4's place. And that gives us -4. And again, you could do that for any of these. You could do that for the -3, you could do that for the -2, the -1, any of the negative numbers, and you'll see that it comes out to the correct result here on the right, if you sort of do that calculation with the binary numbers. Now, the next thing I want to move on to is floating point types, but before I do that, you're probably asking, and I mean maybe not, but I asked the question, why is it called 1's complement? Why is it called 2's complement? Why is it, how does it get that name? Well, 1's complement and 2's complement are actually both examples of what's called a, let me write that here, is actually called a radix complement. Now radix basically just means the number of unique numbers we have in a certain base. A certain numerical base system. So, for example, in decimal, which is what we use day to day in our everyday life, that would be base 10. And it's and so the radix of that would be 10 because we have the numbers 1 through 9. We can use the numbers 1 through 9 in each place, in our tens place, in our hundreds place, in our thousands place, in our 10,000s place, whatever. We have 10 different numbers, meaning 0 through 9, that we can put in each place in our base 10 number. So binary, for example, would be base 2 because we have 0 or 1. We only have the option between using two different numbers in binary in each place, in our 2's place, our 4's place, our 8's place. So we only have 0 or 1, and so the radix would be 2, because we only have two different unique numbers we can use in each position. So how do we go about calculating the radix complement? So let's write down again, radix, say radix, I'll just write comp, radix comp. And so how we do that is, let's work in base 10 for an example to start off. So let's say we have the number, we'll just make it simple, let's say we have the number 7. Say we have the number 7 in base 10, which again, base 10 is the normal number numerical system that we use in our day-to-day life. So we're going to label this, and we'll say n equals 7. We're going to label 7, we're basically going to represent 7 by the capital letter N. So we have a number 7 in base 10. Now if you notice, 7 is a single digit, it's just one digit. So we're going to write another symbol here, which is lowercase n, and we're going to set this equal to the number of digits in n, which is a single digit, so we're just going to write 1 here, representing that capital N is just a single digit. And then we're going to write one more symbol, r. And what r is going to represent is r is going to represent the base that capital N is in, which we know in this example is base 10. So we'll say base 10. So here we're going to write r equals 10 since it's in base 10. So I know we were talking about 2's complement a little bit ago, but when we're talking about base 10, what we're actually talking about in base 10 is 10's complement. 10's complement. So the you can basically just replace the word radix here with whatever base you're working in. So since we're working in base 10, we replace radix with 10. So we write 10's complement instead of radix complement. And so basically what we're trying to do is we're trying to find a missing number where, and we'll call our missing number, let's just call it, we'll just call it x, some basic math symbol. We'll call it x, x equal to, we don't know what x is yet. That's what we're trying to find. And so basically what we're trying to do though is we're trying to find what number, meaning x, what number added to n, which is our 7, so n plus x, what number would equal r, which is our r right here, which is 10 in this case, to the nth power. So which number added to 7 would equal r to the nth power, which in this case would be 10 to the first. So let's fill in all the variables that we can here. So we say 7 plus x equals, we'll say 10 to the first power. So we basically need to figure out what number x here would make this statement true. And so we're going to move this over and we're going to simplify this. We'll say 7 plus x equals 10, because 10 to the first power is just 10. And then what we can do is move it over again and we'll say x equals 10 minus 7 if we just subtract a 7 from both sides. And finally we come to x equals 3. So in this case, 3 would be our 10's complement in this case. So to write this a different way, because this is the way you'll see the formula most often, it'll just be r to the n minus uppercase n equals, and again we'll just say x again in this case, equals x. We basically need to solve this equation in order to get our 10's complement for n. And you can see that r to the n minus n is really just this part right here. So we could really just fill in a 1 here, like we had over in this step. But it would just be 10 to the first minus 7 equals x. So that's really where this r to the n minus n is coming from. And basically then what we're doing, because r to the n, so for example, if instead of a 7 here, instead of a 7, maybe we had a 17. Maybe we had a 17 instead of a 7. So now we have 2 digits. So this would change the whole structure of this equation, or I should say the numbers within the equation. The actual r to the n minus n stays the same. So our lowercase n in that case would change to a 2. Since we now have 2 digits, 1 and 7 in our base 10 number. R still stays the same because we're still working in base 10, so R still stays the same. So you notice here that if we wrote out again our equation of r to the n minus n, so we'll just go up here real quick and we'll write it out of the way. So we'll say 10 now to the second minus 17 equals, and we'll put a question mark there. So 10 to the second, 10 squared is really just 100 minus 17, which this equals with 83, so equal 83. And so 83 in this case would be our 10's complement to 17. So, if you think about powers of 10, and I'll just start from 10 to the first, because 10 to the 0 is just 1. But if we think about powers of 10, 10 to the first, 10 squared, 10 to the third, this is just 10, 100, 1000. And so really all we're trying to do in the case of 10's complement is, whatever number we have here, which in this case, this last example we just did was 17, we're just trying to figure out, what number added to this number would basically equal 10 to the number of digits, 10 to the power of the number of digits we have in the number, which again, 17 is 2. That's why we were using 10 squared in our equation here. So basically just trying to figure out what number plus 17 would equal 100, and that would be our 10's complement for 17. So let's switch over to binary now. So let's switch over to binary, and again we know that binary, we'll say binary is base 2. Base 2 again because the radix of binary is just 2, because again we can only have 0 or 1 in each position. in each position in our binary number. So because it's base 2, the radius complement would be called 2's complement. Again, because 2 is our base. So let's write 2's comp. 2's comp. And so let's do an example like we did above, where we had define our radius complement, where we had n, or uppercase n, lowercase n, and r. Let's do another example just like that. So let's say we had a binary number, which would be represented by capital N. We'll make it simple. Let's say we had a binary number that was 0, 0, 1, 0, which we know in base 10 in decimal, this is actually equal to just 2, because we have a 1 here in our 2's place for binary. And then our lowercase n in that case, our lowercase n would be 4, because we have 1, 2, 3. All right, make sure I write arrows here. 1, 2, 3, and 4. We have 4 digits in our binary number here. So our n would be equal to 4, just like how for 17 we had 2, and for 7 we had 1 for our n. In this case we have 4 digits, 0, 0, 1, 0, so lowercase n is going to be equal to 4. Let's say then that we had our r, and of course since we're working in base 2, our r is going to be equal to 2. And again we'll write x for the number that we're looking for the 2's complement that we're looking for. So let's set up our equation that we had before. If you remember above, it is r to the n minus n, and in this case we'll say equal to x. Could just write a question mark there, but we'll put x since we use x down here. And so let's fill in the numbers here. So our r, it's working in base 2, is going to be 2 to the nth power, which is 4, lowercase n that is. And then we're going to subtract 0, 0, 1, 0. And so before we solve this equation, let's figure out exactly what we're trying to do here. I'm going to put equals x here just to finish that. But let's figure out what exactly it is we're trying to do. Let's think about what it is that we're trying to find here. So since our binary number has 4 digits, if we think about the original equation we wrote out, where we have n plus x equals r to the lowercase n, what we're really trying to do here is we're trying to find the number x that will, a number x such that adding n, capital N to it will equal r to the n. And so if we finish the 2 to the 4th here below, simplify that out, we have 2 to the 4th, this is equal to 16. And so what we're really trying to find then, and let's fill in our capital N here, we're trying to find a number that when added to 0, 0, 1, 0, which is our n, which is just 2 in base 10, if we converted that to decimal, what number added to 0, 0, 1, 0, so we'll say plus x, which is the number we're trying to find, would be equal to 16, or if we converted that to binary, 1, 0, 0, 0, 0. So essentially what number added to 0, 0, 1, 0 will get us to 1, 0, 0, 0, 0. And so let's take this and let's go back down to the equation we were working on here below. And so the first thing, let's again simplify out our 2 to the 4th, which we solved above, which is 16. So we have minus 0, 0, 1, 0 equals x, which is again is the 2's complement number that we're looking for. And so I really should have done this part first probably, but since 16 is really our 2 to the 4 here in the equation above, and then 2 to the 4 is really our r to the n in this equation, ultimately we wanted to get it into this form like we had before, because this is the form you'll see most often, r to the n minus n equals rx, which is the number we're looking for, the missing number we're looking for. So you can see here that this equation here is really this equation, r to the n minus n equals x, where 16 is really our r to the n, 0, 0, 1, 0 is then our uppercase n, which is a number we already have, and we're trying to find x, which is the 2's complement. So if we take this down one step further, let's convert 16 now to decimal, which we've already, or excuse me, to binary, which we've already done over here. So we just have 1, 0, 0, 0, 0, minus 0, 0, 1, 0 is equal to x. So now we just do some basic binary subtraction. So we would have 1, 0, 0, 0, 0 subtracted from, or I should say, now we subtract from that 0, 0, 1, 0. So we have 0 minus 0, which is just 0. Now here we have 0 minus 1, so we actually need to somehow borrow 1 from over here. So we're going to cross this out. I'm going to put a 0 here, and then this right here becomes 2. And I think I did this earlier in the video, and I didn't explain why this is a 2 exactly. So if, just real quickly as a little side tangent, if you're doing something in base 10, for example, where you have maybe, let's say you have 11 minus 9. So just like how in base 10 in ordinary subtraction, if you were doing it like this, I mean, obviously we know 11 minus 9 is 2. But if you were writing it out like this and you were showing your work, we have 1 minus 9 here, and we know we obviously can't do that, so what we do is we would cross this out, this would become a 0, and then we would add 10 here. We would basically add 10 to the next place over, because each time you move to the left, the position is actually, the value of the position is basically 10 times more than the position to the right, which is why it's called base 10. Since we would add 10 here, we have 11, and then obviously this would just become 2 ultimately for the result here. But since in binary working with base 2, when you borrow a value, so here for example, how we borrowed from this 1 at the end of our 1, 0, 0, 0, 0, this became a 0. When we move it to the right, it becomes a 2 because we're in base 2. So it becomes a 10 here, or I should say we add 10 to the place to the right since we're in base 10 here. But since we're in base 2 with binary, we would basically add 2 moving to the right when we borrow a 1 from the left. So I'm going to go ahead and cross this out. We're going to make this a 1, so we're going to borrow another 1 and move that to the right. So this would become a 2 here. Cross this out, another 1, and now this becomes a 2. And so we have 1 minus 2 now, or pardon me, we have 2 minus 1 now. So this would just become a 1. 1 minus 0, which is 1. 1 minus 0, which is 1. And then finally we just have 0 here. And so ultimately, here is our result. So we would say this right here, 0, 1, 0, 1, 1, 1, 0, is ultimately equal to x. And so in other words, if we convert this to decimal, base 10, we could say x equals, and this would be, we have a 0 in our 16s place, so that would be, we wouldn't add anything there. We have a 1 in our 8s place, so we have 8 plus 4, which was a 1 in our 4s place, plus 2, plus 0, because there's a 0 in our 1s place. So we would have, this is equal to 8 plus 4 plus 2, and ultimately x equals 12, it equals 14. X equals 14. Let me make that a little cleaner here so you can see it. X is equal to 14. And so if we think way back to the beginning of what we were trying to find, we were trying to find our x. And our x was basically the number such that adding 0, 0, 1, 0, which was our original number, to it would give us 16. And since 0, 0, 1, 0 equaled 2 in base 10, and we can now fill in a 14 for our x here. So our x here would be 14, well, 2, our 2, plus our 14, that ultimately equals 16. So 14 is our 2's complement to 0, 0, 1, 0, or otherwise 2 in base 10. And so in summary, that's why it's called 2's complement. We really didn't need to go into all this detail of why exactly it's called that, but to me it bothered me that I didn't understand why it was called 2's complement for the longest time. But that's really the whole reason, is because if you look back to the original equation here that we were solving, 2's complement refers to the r right here, which is our base. So 2 to some power, given that we already know, that we have one number, which in our case was this n here, capital N, which was 0, 0, 1, 0. 0, 0, 1, 0. What number added to this number would give us 2 raised to the power of the number of digits which in this case was 4, just 4 here. But that's basically why it's called 2's complement, because we're always looking for the complement to the number that would give us basically this value. And likewise, 10's complement, 10's complement, if we had 10 to the 1 equals, we could say, 7 plus some number x. There's only one digit in 7. That's why we have a 1 here. So it's called 10's complement because now we're in base 10 now. And so we're basically just looking for the complement of 7, some number that's a complement of 7 that would added to 7 would equal 10. And of course, if 7 had two digits, so 17 instead, then we're looking for some number x that would then equal to 2 squared. So we're looking for the complement of 17 such that adding the two numbers together, 17 and its complement, would equal 10 to the power of the number of digits in 17, which 10 squared is 100. So we're looking for two numbers basically that equal 100. And so if you remember before, when we were working with 2's complement, the practical way we got to the 2's complement of a particular binary number. So for example, let's say we had just a 1, so 0, 0, 0, 1. To convert this into 2's complement, we would basically flip all the bits, so we'd have 1, 1, 1, 0, and then we would add 1 to this whole binary number. And so we would add 1, so we would end up having 1, 1, 1, and 1. And this would be the 2's complement of this number. And so what this 2's complement actually represented then was -1. So if this equaled +1, if 0, 0, 0, 1 equals +1, the 2's complement would equal the negative of that number, so a -1. And so, if we did 1 plus 1 plus a -1, we know this would be 0. And so likewise, if we did 0, 0, 0, 1 plus, we'll say 1, 1, 1, 1, which again, remember, this is 1, this is -1. And so we would have, we would basically add these then. We'd basically adding +1 to -1. And so we would get, here we would get 0, carry the 1, we get 0, carry the 1, 0, carry the 1, 0, carry the 1, this would be 1. Since we're working with only 4 bits, we would basically just forget this carry bit, and we're left with 0, which is exactly what we expected, and just like what we got over here in our decimal addition calculation where we added 1 to -1. And so likewise, and I'm going to run through this equation really quickly, again, if we used our r to the n minus n equals x, which again, x being our 2's complement number, if we again use this equation and we filled it in for 0, 0, 0, 1, we would have base 2, so 2 to the n, which would be 4, because we have 4 digits, 4 binary digits, minus n, which would be 0, 0, 0, 1. And we'll quickly do this, so we'll have 16 minus 0, 0, 0, 1. 0, 0, 0, 1. We will bring this up here. We have, converting 16 to decimal, we have 1, 0, 0, 0, 0 minus 0, 0, 0, 1. So we would have 1, 0, 0, 0, 0. Subtract from this 0, 0, 0, 1. And so we need to borrow 1 all the way over here from the left. Left with 0. Here we're left with 2. Cross that out, a 1. We can bring a 2 here, cross that out, get a 1. Bring a 2 here, cross that out, get a 1. Bring a 2 here. And so here we are left with 2 minus 1, which is 1. And then 1 minus 0 is 1. 1 minus 0 is 1. 1 minus 0 is 1. Here we're left with 0 at the end. And you can, so basically you can see we have 1, 1, 1, 1 essentially, which is what we came to as our 2's complement when we did it the way we learned before, sort of the shortcut way to get to the 2's complement number. And so I really just did this to show this to you, to sort of show you what's really going on when we calculate this number using sort of the shortcut methodology. This is really what's going on under the hood, is we're basically finding the number that complements this capital N, whatever number. So in this case, it'd be 0, 0, 0, 1. Basically, the number that would complement this number in order to get base 2 to the power of however many digits are currently in the binary number, which in this case is 4. But the way of using this formula, sort of showing exactly what 2's complement is with this methodology here, is just a little bit more of an explicit way to show what's going on. So the last thing I want to talk about in this video is how floating point numbers are represented in binary. So when we think of floating point numbers, we usually think of things like 2, .02, 1.11, 0. I don't know, 46. And so these are all examples of floating point numbers. But we can also represent floating point numbers in scientific notation. So if, for example, we had a number that was something like 2.0201, or maybe to make this a little clearer, what if we had something like 202.01, and we'll go ahead and get rid of this top number here. So if we had something like 202.01, we could represent this in scientific notation. And again, remember, just to make this clear, right now we're working in base 10. I know we were just talking about binary a little bit ago. Right now we're working in base 10. If we had 202.01, we could represent this in scientific notation as 2.0201 times 10 to the, we would implement this over, so times 10 to the second. Now, I'm sure many of you have worked with scientific notation before, but basically how it works is if you look at this exponent here we have on the right side of the time sign, and we'll talk about the names of these two parts here in a second, but if you look at that exponent here for the 10, basically if this is a positive number, you would move the point here that many places to the right if it's a positive number. If it's a negative number, you'd move the point that many places to the left. The decimal point, that is. So since in this case it's a positive 2, we would move this 2 places to the right. So this number would actually be 202.01. This number here, 202.01, equals this. This is just its scientific notation representation right here. Likewise, let's say this was a negative 2. In that case, this would actually move 2 places to the left, so this number would actually represent 0.02. Let me actually get rid of the 0 here. 0.020201. This would equal the same thing as this if this was a negative 2. And so it would no longer be equal, just to avoid any confusion here, it would no longer be equal to this. Instead, it would be equal to this, since we move the decimal place 2 places to the right, over 1, which means we would have a 0 here, so it would go 1 spot, 2 spot, and that's how we get to this number here. And so if we write out this number again that we had before, so we have 2.0201 times 10 to the second. So the part on the left side of the multiplication sign here, this is what's known as the mantissa. And I'm going to try to spell this here to the best of my ability. If I spell it wrong, you will probably see an edit pop up in the video. But this is what's known as the mantissa. Now the part on the right of the multiplication sign is what's known as the exponent. The exponent. And these are the two exponent. These are the two parts that make up the scientific notation representation of a number. And now when we store floating points in binary on a computer, this is actually the representation that we use, scientific notation. This is actually the representation that we use, except it's basically translated into a binary encoding. So when we store these floating point numbers in binary on a computer, we actually use what's called the Ieee 754 standard. Ieee 754. And so this is basically just a standardized way, again, of storing floating point numbers in scientific notation, essentially, on a computer in binary. So I actually have the book Digital Design and Computer Architecture, second edition, in front of me by David and Sarah Harris that I'm kind of using to talk through some of these floating point concepts, floating point number systems. But I think there was a small revision in 2019 to the Ieee 754 standard. I don't think it's going to affect any of the things we're going to talk about today. I think they were just, the revisions were relatively minor, but I would recommend maybe going and just doing a quick Wikipedia search for the 2019 revision of the Ieee 754 standard, if you so wish to do so, just to see what those revisions were and how it maybe can enhance or how it did enhance the Ieee 754 standard when we store floating point numbers on a computer. And so again, for floating point numbers, there's really three relevant parts. I should say floating point numbers, how we store them on a computer. There's really three relevant parts to the floating point number. First of all, we have the sign. We have the sign, meaning whether or not the number is positive or negative. We have the mantissa. Which is basically the fractional part that we saw here, the fractional part here of our number. So like in scientific notation, for example, if we had 1.04 times, we'll say we're in base 10 times 10 to the second, this would be the mantissa, again, the fractional portion here, the decimal portion here. We also have the base that we're in, So again, in this example, you can see the base right here. We're in base 10. We're in base 10 here for this floating point number. That is in scientific notation. And then we also have the exponent, which exponent again is just this little number here at the top. That tells us how many places to shift, either left or right, in our mantissa here. And so ultimately then you end up with the form for any floating point number in scientific notation of plus or minus. And again, we'll use m for the mantissa, and then we'll go times b to the e here, which is our exponent. So basically we have plus or minus mantissa, positive or negative mantissa, times the base to our exponent. And yes, this is a b, contrary to what is probably popular belief. Let's go ahead and see how the Ieee 754 standard represents these numbers in binary. So for floating point numbers in the Ieee 754 standard, to the leftmost bit, there is a single bit, and we'll just write 1b. There is a single bit, and this is what's known as basically the sign bit. Let's make this be a little bit better. This is what's known as the sign bit, and this can be, again, a 0 or a 1. If you remember from sign magnitude and 2's complement, if this bit is a 0, it's positive. If it's a 1, it's a negative. And by positive or negative, we're talking about the entire floating point number here, the entire floating point number. So this, the sign bit basically represents this part right here of our, if we're thinking about this in terms of scientific notation. So again, 0 is positive, 1 is negative. Now to the right of the sign bit, we have 8 more bits. And here I'm going to write below here is sign, so just ask for sign. These 8 bits here represent the exponent. And so we're talking about this portion here now, the exponent here, right here. And you're probably wondering what happened to the base. Well, the base is basically implicit, or it is an explicit by just looking at the numbers. So since we have 0, 1, only 0 or 1s to work with, we're in binary, we obviously are in base 2. But again, these 8 bits here are referring to the exponent here. Now the exponent portion of our floating point numbers is actually unsigned, and so you're probably wondering, how do we represent negative exponents? Well, we use what's called a bias, and we'll see that here in a little bit. And so to the right of the exponent portion, we actually have typically what's the longest part of the floating point number in binary, and that is the mantissa. That's the mantissa. And so standard is that this is usually, this is 23 bits. And so again, the mantissa, we're referring to this portion of our number right here. Just to make this clear, I'll also make sure to draw our sign bit over to what we're talking about. And so essentially, this is how a number is represented in binary via the IEEE 754 standard. And I shouldn't say number; I should say floating point number specifically. And so just a couple things I want to talk about regarding the Mantissa portion. So again, if you remember, we had the sign bit portion here. So sign bit, which was just one bit in total. Then we had the 8 bits here, which this was referring to the exponent portion. And then finally we had the Mantissa portion here at the end, the IEEE 754 standard. And this was typically 23 bits. 23 bits. This was the Mantissa portion. So when talking about the Mantissa here, we're not going to do any crazy, we're not going to go into any crazy formulas like we did with choose complement. We're not going to talk about really addition of floating point numbers. I'm going to link some resources down in the description below that you can kind of go through from different authors on YouTube. But the main point I just want to get across is kind of how floating point numbers are represented in binary, because when you go to do the addition, you're really just adding the mantissas together, and there's a few extra steps you got to take with getting the exponents in the right, or in the correct base, using the same number, or the same number for the exponent and stuff like that. So there's a few extra steps to it, but again, I'll be linking some resources in the description that you can walk through some problems like that. But when talking about the Mantissa, before I had a number, I think that was like 1.101 or something, something like that. So I just wanted to mention that when you have a binary point like this, so this should be a decimal point in base 10, but again in base 2 it's called a binary point. When you have a binary point like this, so how this right here would technically be our ones place, and then if just for example, if we had another one here, this would be our twos place, and then our fours place, and so on and so forth. When you get to the right of the binary point, you actually, so if you see here, we're almost having it every time, where 4 to 2 is basically 4 divided by 2, 2 divided by 2 is just 1, and really it's more about the powers of 2 than having, but just to kind of think about it this way. So when we move to the right of the binary point, we actually just continue having. So when we go to the first binary number, the first bit, I should say, sorry, the first bit to the right of the binary point, this is actually going to be 0.5. Then if we move again to the right, this is going to be 0.25 here, and then that basically just continues all the way down past the binary point. You just keep on going and going. Now, one of the interesting things is that you'll see that because it has like this every time, we can't represent every single decimal number in binary. That's why there's many weird rounding errors and we'll see that later on in the C++ code. But there's many weird rounding errors that happen, and it's because in binary we can't represent exactly every single decimal number that we can in base 10, for example. So that was one thing I wanted to talk about regarding the Mantissa. Another is that the Mantissa will always be a normalized form. And when we say normalized form, here's what we mean. Let's just say we had a random binary number. We'll put 0, 0, 1, 1, 0, 1, 1, 0. This is a totally random number. Has no relevance at all. But if we wanted to put this Mantissa, let's say this is our Mantissa, if we wanted to put this in normalized form, basically normalized form is always going to put the binary point, so this guy right here, the binary point, one spot to the right of the first one in our binary number, if we're looking from left to right. So if we started on the left and we went over and we found our first one, the binary point will always will always be to the right, just one spot to the right of the first one. So we can basically at that point forget about these leading zeros here in our binary number, because they really add no value to the number itself. And then we can just consider this, and this would be our normalized form. Now remember that anything to the left of the binary point would basically result to a decimal, or I should say an integer, a whole number, if we translated it to decimal, to base 10. So this 1 would mistranslate to a 1, essentially, because this technically would be our 1 spot right here. And then of course anything to the right of the binary point, as we saw above here, is going to be first one would be 0.5, then 0.25, and so on and so forth. But the important thing to note is that when we put the mantissa in normalized form, the leading one, the one to the left of the binary point, I should say the bit to the left of the binary point is always, 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 always going to be 1. It's always going to be 1. So knowing that we're in normalized form, and we know that the first bit to the left of the binary point is always going to be 1, we can then basically say that we can just kind of forget about this 1. We can just sort of forget about this bit here and just implicitly consider it still being there. And the reason being that we can do that is, number one, we always know that the first bit in the mantissa is going to be a 1. And also what it does for us then is that we can actually tack on another bit then to the fractional portion of our mantissa, increasing both the accuracy and precision of our number. So if we let's just say we had a number like 1.001, well, since we know that this is always going to be a 1 in normalized form, we can, when I say forget, I don't mean that we don't use it at all. After the fact, we add it back on. So we know that this is just going to be a 1, so we can add it back on after the fact, after we're done with our, our floating point addition or whatever it might be that we're doing. But we can implicitly consider it being there, so we can basically take it out of one of the 23 bits of our mantissa, and we can shift everything to the left. So this would end up looking, if I could draw an arrow here, something like 0, 0, 1, 0, with this extra 0 here tacked onto the end. Now, if we wrote out 20, all 23 bits, the fractional portion, right, that's to the right, let's say our binary point was right here, our fractional portion here to the right of the binary point would be 22 bits of these 23 bits if we still had included our original 1. But since we're getting rid of this 1, we can now represent the entire fractional portion of the mantissa using all 23 bits, So that increases, again, both the accuracy and the precision of the mantissa itself. And so one of the other things I wanted to talk about was the bias. So if we hone in real quick here on the exponent portion of our floating point number here, we're going to bring it down here to show our work. So since it's unsigned, we know that all the values are going to be greater than or equal to 0. So how then do we represent negative exponents with our 8-bit binary number, or I should say our 8-bit unsigned binary number? Well, we do that by using what's called a bias. So if you think about how many different values 8 bits can represent, we can really calculate that by saying what is 2 to the 8th power. That would be equal to, and let's go ahead and use our calculator here, that should be 256, I believe. So let's do a clear all, and we'll go to the 8th. So we have 256 different values that we can represent with 8 different bits. And really what that is, our range is really anywhere from, we'll write 256 here, 256 different values. But that's really the range from 0 to 255, 0 to 255. So what we can do with a bias is, normally what you want to do with the bias here is we want to basically try to find a number that's right in the middle of this range, which in this case would basically be 127. So the reason we take this bias to be 127, and what the bias does for us, is that it basically takes the range from being 0 to 255 to now taking it to be negative 127 to positive 127. Excuse me, this is actually positive 128, not 127. And so the reason being is because, let's say our exponent, so remember again, it was 8 bits. Let's say our exponent was 0, 0, 0, 1, 0, 0, 0, 0. We know that this right here is just 16. This is just equal to 16. And so with an unsigned 8-bit binary number, this would be our exponent for this specific floating point number would be 16. Well, what we can do with the bias is once we calculate our exponent from here, what we can actually do is do 16 minus 127. Minus 127. And so this is going to give us, and I hate to say it, but I'm going to use my calculator just to make sure I'm correct here, 16 minus 127, that's going to give us negative 111. So really, when we see this, we no longer consider our exponent to be 16, we actually consider it to be negative 111. Likewise, let's say we had all 1, so 1, 1, 1, 1, 1, 1, 1, 1, which we know this is equal to 255. Well, instead of being the exponent 255, what this is actually going to be, let me scroll down here a little bit, this is actually going to be 255 minus 127, which again, let's use our calculator, no shame in that. We'll go 255 minus 127, oh, we got 255 minus 127, and we get 128. 128. So this is actually going to be the value of the exponent for this number here. So you can see then that the maximum exponent we can have that's positive is 128, and the minimum then is going to be negative 127, and that being because the minimum exponent and then normally would be 0, 0, 0, 0, 0, 0, 0, 0 with an unsigned binary number, which is equals 0. What we would really do is take 0 minus 127 to get negative 127. So here is the smallest, or the least exponent that we can have. So that's why our range then, because if this is the max, this is the minimum, that's why we have our range here, negative 127 to 128, when 127 is our bias. And so, 127 doesn't have to be the bias. You can really make the bias anything you want. 127 is this kind of standard for, typically you want to find a number that's right in the middle, so you can kind of make the even and positive numbers you can represent about split even. But you can make this anything you want. You can make it 100, you can make it 200, you can, anything in the range of 0 to 255. And that would then shift this range accordingly, depending on whether you made the number larger or smaller, negative, positive, whatever it might be. And again, this video is starting to get pretty lengthy, so I'm actually going to not go over how to add and subtract floating point numbers. I'm going to put a link to a description in the video below that will lead you to another video by a different YouTube author that walks you through how to do that. And he does a very good job. Goes through a lot of examples and even gives some self homework problems that he'll walk through with you at the end. So I would highly recommend watching that if you're interested. But I just wanted to understand how these floating point numbers are represented in binary, so that way when we get to working with them in floating point numbers in C++, we're not lost. We're not completely lost. We're not just like blindly, without understanding how these floating point numbers are stored in memory under the hood. I think it's very good to have that mindset, because that way when we're working and we get these weird rounding errors or we get these weird precision errors and stuff like that, we know why, we kind of have a general understanding of why that might be the case. One last thing I wanted to show here, I'm just grabbing this because this is actually comes from the book that I'm reading. So this table kind of shows us some special cases with floating point numbers, excuse me, in binary in the Ieee 754 standard, as you can see from the description of the table. So to represent certain numbers, there's certain special cases with the exponent and the mantissa in order to represent those numbers. So to represent the number 0 for a floating point number, basically the sign can be either or, but the exponent is going to be all 0 and the fraction is going to be all 0. And that would represent 0 for floating point numbers in Ieee 754. To represent infinity, the sign is 0, and then the exponent is all 1s, and then the fraction is all 0s. Likewise, negative infinity would just be a 1 for the sign, because again, 0 is positive, 1 is negative, that makes sense. And then we have all 1s for the exponent, all 0 for the fraction, for the mantissa portion, just like positive infinity. And then NaN, which just stands for not a number. Basically, if somehow something is getting represented in floating point that ends up not being a real number or a number that we can represent, basically the sign can be either or. The exponent 8 bits would be all 1s, and then the fraction would basically just be some non-zero number, or the mantissa, I should say, is going to be some non-zero number. So again, just some special cases. You could easily Google that and find that if you ever need to look it up and reference it, but just thought I'd show that since we're talking about it anyways. And so that's basically all I wanted to talk about for floating point numbers. There's more things we could get deeper into, like how rounding works with floating point numbers. Since floating point numbers can't represent, at least in binary, they can't represent, again, every number that you and I could represent on pen and paper. They round in certain circumstances, which is why sometimes you see, like when you we'll see if if we add two floating point numbers together in C++, for example, or subtract, they might not always come out to the exact value that we would expect. And then, of course, you can do things like adding and subtracting floating point numbers in binary. And so I was going to go over briefly how code is, code like C++ is translated to intermediate code, machine code, and then is basically then translated to binary and such. I was going to briefly go over that and give a high-level overview of how that works, but seeing as how long this video has become, I think I'm going to stop it here. But if you stuck around this long, I went back when we were talking about how binary relates to data types, and I realized I forgot to mention Boolean. So as a little Easter egg here, if you stuck around this long, if you think about what a Boolean is, a Boolean is either true or false. It's going to be true or false. So we really only need one bit to represent this, because we can represent true with 0, we can represent, we can represent true with 1, we can represent false with 0. So that essentially wraps up this video. I know this is incredibly long. I'm sure after the fact I'll wish I'd split this up into different videos to talk about sign magnitude, 1's complement, 2's complement, floating point, binary relating to data types all separately. But I just decided to kind of compile all this into one video to get it all into one place. And so hopefully you learned a lot from this video. Hopefully now when we talk about binary in the future, it'll make a little bit more sense when we talk about it in terms of how we work with it in C++. And yeah, that's pretty much it. I'm going to end it there, and next time we will jump back into actual C++ code. So I will see you then. Thank you.